the results compared to the present state of science. The practicability of a new hypothesis is defined by how it fits into the scientific results observed up till that time. With regard to this, we consider it important to analyze and interpret our results from two aspects: the possible role of deuterium as a mass number 2 isotope of hydrogen in regulation from a chemical aspect, and b. the possible connection of the change in D concentration with the known signal transducing systems. We think that the effect of deuterium from a chemical aspect has been amply studied during the past 60 years. From the vast inventory of knowledge, we wish to point out those which may be of significance in justifying the role of naturally occurring deuterium in biological systems. The concentration of deuterium is 12 to 14 pL in living organisms. Deuterium behaves differently from hydrogen in chemical reactions. This can manifest itself in enzyme reactions as well, as for example, Kn may alter between 5L5 and 10. Deuterium bond is stronger than hydrogen bond. This quality of deuterium is manifest in biological systems as well. Great deconcentration is expressly toxic. Certain enzymes and processes are able to differentiate between the two variants of hydrogen in favor of hydrogen. Be irrespective of our theory, from among the results accepted in our days in connection with the regulation of cell division, we should highlight the following. Prior to cell division, the NAD+/H+ transport system becomes activated in the cell membrane. This drives H+ out of the cell while taking up NAD+22. In the course of this process, intracellular H+ ion concentration decreases, pH increases, which is a commonly observed phenomenon prior to cell division, and is said to be in a cause-effect relationship with the start of cell division. Numerous experiments confirm the conclusion that the activation of the NAD+H+ system is indispensable for the start of cell division. Mutant cell lines were produced in which the NAD+/H+ transport system failed to work. It was found that as a consequence of mutation, the cells lose their ability to divide at acidic and neutral pH values 23. The defective growth factors was examined to find out through what mechanism the cell division signal gets transmitted. These experiments showed that growth factors activate the NAD+H+ system. The connection between the activated NAD+/H+ system and the cancerous character of the cell line was proved by two series of experiments. Firstly, it was stated that in a cancerous cell line produced via mutation, the pH increased compared to that in the initial cell line 24. Further, a direct connection was found between the functioning of oncogenes and the shift in intracellular pH value, because the injection into a cell of the protein coded by the HRAS oncogene or the expression of the VMOS and HRAS oncogenes also shifted the pH of the cell towards an alkaline character by activating the NAD+/H+ system 25, 26. Beside the NAD+H+ system, the activation of another H+ transport system initiates similar changes. In these experiments, the ATPase gene was isolated from yeast, and this was used to transform a murine and a simian cell line. Gene expression and its product, ATPase, continuously extruded the H+ ions from the cell, which resulted in intracellular pH increase. The really astonishing result of the above experiment was that cells transformed by the ATPase gene of yeast became carcinogenic. 27. These experiments point out that to initiate cell division, the activation of a system through which H+ ions are extruded from the cell and thus increasing the pH is indispensable. It is important to note that the artificial increase of intracellular pH did not seem to be sufficient to stimulate cell proliferation. 28. Thus another process, for example the shift of the DH ratio, must play a role in the transduction of cell division signals. Conclusions. During experiments carried out in the past years, we have been changing the D content of the medium in various biological systems. We experienced that in every single case the decrease of the D concentration induced significant changes, proving that living organisms, which, through millions of years have become adapted to a D concentration of about 150 ppm, are able to perceive the lack of deuterium. Considering our knowledge about deuterium and the achievements of molecular biology in the past decades and also the observations of our experiments with deuterium depletion, we have set up the following hypothesis on the regulatory role of naturally occurring deuterium. In higher living organisms, over millions of years, a regulatory system has developed which is sensitive to the intracellular changes in the DH ratio. The DH ratio can increase in cells if one of the H+ transport systems H+ ADPase, NH+ antiport system gets activated in the membrane. This process prefers H+. Thus H+ and D+ get ejected from the cell or organelle, for example, mitochondria, not in proportion to their ratio of occurrence. The consequent intracellular change in the DH ratio is perceived by certain enzymes, because through the shift in DH ratio D+ is more likely to bind to a given place in proteins. The D+ bond may stabilize the conformation of the protein, rendering it either more or less active, and this ultimately has an effect on its function. From this point on, the signal continues its way through the already known of hitherto undiscovered molecular systems and creates the well-known cell biological phenomena, such as, for example, cell division. In our view, the validity of the hypothesis is reinforced by the references in literature and proved by experiments carried out with DD water. On the basis of our achievements, we presume that the application of DD water offers a new therapeutic possibility for clinicians complementing existing anti-cancer treatments to treat cancer more efficiently, and the preparation may play a role in prevention. 2. References. 1. Isotope reflex chemical reactions Collins C. and Bowman and S. eds. Van Nostrand Reinhold, New York, 1971. 2. Jankso, G. and Van Hook, W.A. 1974 Chem. Reference 74, 689-750. 3. Jamieson, C. Isotologies in the Physical and Biomedical Sciences Vol. 2. Boncelli and Jones, R. eds. Elsevier, Amsterdam 19914. Annals of the Newdvork Academy of Sciences 196084. 573-781. 5. Rundle, P.W. Elleringer, Rand-Nagy, K.A. Stable Isotopes in Arola Gyro Research, Springer, New York 1988. 6. Katz and Crespi, H. Shell Isotope Effects in Biological Systems. In Collins, C. and Bowman, in SCDS Isotope Effects in Chemical Reactions. Van Nostrand Reinhold, New York, 1971286363. 7. Yurtsever, Y. and Gat. R. Stable Satalies Hydrology Gat. Rangon Fiantini R. eds. International Atomic Energy Agency, Vienna 19811033142. 8. Siegler, H. Osman, C.B., Stichler, W. Treenborn, P. 1976 Planta 128, 85-92. 9. Estip, M.F. and Horing, T.C. 1981 Plant Physio, 67, 474-477. 10. Katik, Bay, Dvorakova, M. and Korita, 1990 Febslet, 264, 203-205. 11. Samli I. G., Jankso G., Jackley G. Y., Vass K., Barna B., Lakix B., and Gall T. 1993 Febslet. 317, 124. 12. Silly IG, Jinksoji, Jackley Y, Lask IG, Galbix Z, Galbix G, Kiss AS, and Birkin ET 1996 Strumazeg Yog Yasa 10, 29-32. 13. Birkin ED, Simli IG, Jackley GY, Janksoji 1996 Kizalatervslas 3,114,115. 14. Simli I, G, Lask I, G, Birkin E.T., Galbix, Bex, Galbix G, Kiss SA, Jackley GY, Jankso, G 1997 Air Farings Heilken 7, 381-388. 15. Simli I, G, Lask I, G, Birkin E.T., Jackley GY, Jankso, G 1997. Hayes, J.R. and Alalo. DGEDS Synthesis and Applications of Isotogically Labeled Constitutes. John Wiley and Sons Limited. 137-141. 16. Simli I, G, Lask I, G, Birkin E.T., Galbix C, Galbix G, Kiss, AS, Jackley, GY, Jankso, G 1998 Zional, Avunco. 30, 91-94. 17. Simli I, G 1998 Combs Jomenter Medicine 2, 6-9. 18. Levy, G 1997 The FASCBJ 11, 234-237. 19. Smalley, Juan Du Bois, R 1997 Advances in Pharmacology 39, 1-20. 20. Sabaramaja K. Zakim D. Wexler, B.B. and Dannenberg, AJ 1997 PSCBM 216, 201-210. 21. Bellyway, QCS, Galbixi 1997 Novini Termals 46, 447-485. 22. Schuldinger, S. and Rosinger, E. 1980 to PNAS 79, 7778778. 23. Plysegur J. Sardet C. Franqui A. E. Lemaine G. and Paris S. 1984 PNAS 81, 48334-837. 24. Sharon, Desso and Party, IB 1987 PNAS 84, 2766-2770. 25. Hagag Ben Lackle J. C. Graber M. Aronson S. and Viol, MV 1987 Mol. Cell, Biol 7, 1984198. 26. Doppler, W. Jaga, R. and Froner, B. 1987 Gene 54, 147-153. 27. Perona, R. and Serrano, R. 1988 Nature 334, 438-440. 28. Mulliner, W.H. Defies, LHK and Delot, SW 1986 JX, by all. 124, 359-373. Chapter 2. To doctors. A man walking in the forest meets a woodcutter who is arduously trying to saw a trunk into smaller pieces. The man goes closer to see what the woodcutter is drudging with, and asks him, "Excuse me, but have you noticed that your saw is completely dull? Shouldn't you sharpen it?" "I have no time for that, I have to go on sawing."